Hello friends, welcome to engineering tutorial. In the previous videos we discussed about the basic concepts related to signals, such as this definition of a signal, the various types of signals such as analog or continuous time, discrete time and digital, the process of analog to discrete time signal conversion through sampling, and related basic concepts. So in this video we are going to focus our attention on specific elementary signals that we deal with in the analysis of systems. Okay, so the topic of today's discussion is basic elementary signals. So we are going to discuss about certain elementary signals such as, now these signals, these elementary signals, okay, they are also called as standard signals or test signals. Now why they are called as standard signals or test signals? Because these signals, these signal functions, they are applied to an unknown system. Okay, these signals are applied to an unknown system. Okay, unknown system, these signals are applied, and from the output, okay, from the output, the behavior of the output, the type of system is categorized. Okay, the behavior of the output gives us information about the characteristics of this unknown system. Okay, this system is unknown, the behavior of this system is unknown. So this test signals, which we are going to discuss, they are applied to this unknown system, and from the output behavior, the output response, the characteristics of this unknown system are defined. Okay, so some of the basic elementary signals that are used for the analysis of systems are, first is the unit step signal or the unit step function. Then we have is the unit ramp function. Okay, unit step, unit ramp function. Then we have the unit impulse function. Then we have the unit parabolic function. We are going to discuss each of these signal functions in detail. Here I am just listing out what are the elementary signals that we are going to cover. The unit parabolic function. Then we have is the sinusoidal functions, sine, cosine and all the other signal functions belonging to that family. Sinusoidal function. Then exponential function. Exponential function. Now this exponential signal or function can be both real or complex. Okay, we're going to discuss both. Okay, the exponential function can be both real or complex. So depending on the duration, how much time it takes to cover each of this signal function, I think it would take around one video each to describe each of these signal functions. So in this video I think I can cover the unit step function. We will discuss both the continuous time domain and the discrete time domain behavior of the unit step function, and if possible I will discuss the ramp function, otherwise it would take another video. Okay, so let us discuss about the unit step function. Okay, so let us discuss about the unit step function. Okay, unit step function. So the unit step function, it is a signal function which has a constant magnitude. You can write it down. A unit step function is a signal function which has a constant magnitude which is equal to unity, and it exists for positive time. Okay, it exists only for positive time, that is for time t greater than 0. Okay, let us draw the unit step function first. First we are going to discuss the continuous time domain and then the discrete time. Okay, okay, this is t and this, let's say this is ut, the unit step function. Now the unit step function, as I said, it has a constant magnitude which is equal to 1, and it exists for positive time. Okay, like this, constant magnitude for positive time, and for negative time it is 0. Okay, for negative time it is 0. It exists only for positive time, for t greater than 0, and for negative time it is 0. Now if the magnitude of this function is not equal to unity but any other value, let's say a, it has a constant magnitude but its value is some other value other than 1 or unity, then it is only called as step function. As here the constant magnitude value is equal to 1, that's why it is called as unit step function. Okay, let's say we have another signal, it has a value a. Okay, then it will be only called as a step function. It will be only called as a step function, not unit step function. Okay, it will be only called as step function. Here, as the value is equal to 1, the constant magnitude is equal to 1, that's why it is called as unit step function. Now how to represent it? The functional representation of the unit step function, it is represented as ut is equal to 1 for t greater than 0 and 0 for t lesser than 0. Okay, it is actually here t greater than or equal to 0, because at t equals to 0 it is also 1. So it is greater than equal to 0, it is 1, and for t lesser than 0 it is 0. Now there is some confusion also. In some books this equal to sign is absent. It means that the value of ut at 0 is undefined, whether it is 0 or 1. It sometimes it's only given for t greater than 0, 1, for t lesser than 0, 0, and in some cases this is given, means for t greater than or equal to 0 it is 1, and for lesser than 0 it is 0. Okay, so it is a little confusing because it from textbook to textbook it varies, okay, but I recommend you that you go by this, okay. For t greater than equal to 0 it is 1, for t lesser than 0 it is 0, and this and the curly bracket, this is the functional representation. Here this will be the step function, it will be a for t greater than equal to 0 and 0 for t lesser than 0. This is not a unit step function, this is just the step function, okay. Now this is the continuous time domain representation, it is continuous time domain representation, okay. Okay, the signal is continuous, it is defined at each and every instant of time. Now suppose by the process of sampling, okay, following the Nyquist sampling criteria, the Nyquist sampling theorem, which states that the sampling frequency must be greater than or equal to twice of the maximum signal frequency, we take samples of this unit step signal at equidistant time intervals, okay, at equal spacings of time. These are the samples. Suppose we took samples of the signal, let's say this is 2 seconds, this is 4, this is 6, and this is 8. We took the samples. In that case the signal will look like this. The discrete time signal will look like this. All having value equal to 1. This is the discrete time domain signal un, and this is the discrete time n, okay. This is at 2, this is at 4, this is at 6, and another at 8, and so on. This is the discrete time domain representation of the unit step function. Here ut got replaced by un and t got replaced, the continuous time t got replaced by discrete time n, okay. This is the discrete time representation of the unit step signal. Now the representation of the discrete time unit step sequence is given by this, okay. Another important thing which I missed is in continuous time domain, okay, in continuous time the signal is called as signal, okay. In continuous time the signal is called as signal, but in discrete time it is not called as signal, it is called as sequence, okay. Signal means it is continuous, okay. So sometimes people say the discrete time domain signal, but that is not a big deal, but you know this fundamental difference between signal and sequence. Signal represents continuity, so in continuous time the value, the parameter will be called as signal. In discrete time it will be called as sequence, okay. If by some mistake you call discrete time signal, it's not a big deal, but still you call discrete time sequence and continuous time signal, okay. I think by mistake I have also called discrete time signal sometimes, okay. So it's a mistake, but always remember that it is called continuous time signal in continuous time domain, and for discrete time domain representation it is called as sequence. Okay, now the discrete time sequence representation of this unit step sequence is given as un is equal to 1 for n greater than or equal to 0 and 0 for n lesser than 0. Only the t got replaced by n, ut got replaced by un, t got replaced by n, everything else is the same. Okay, so this is the unit step function. Okay, this is the continuous time representation. We took samples of it following the Nyquist sampling criteria, converted into discrete time domain, and this is the discrete time sequence representation, the functional representation of the discrete time sequence. Okay, in continuous time it was ut and t, in discrete time it is un and n, everything else is the same. It has constant unity magnitude for discrete time sequence n greater than 0, means for positive discrete time, and it is 0 for negative discrete time. So this is some of the basic concept related to unit step signal in continuous time and unit step sequence in discrete time. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.